Okay, so I've got this problem up on the board. I want to evaluate the double integral over r of this function, x squared over 9 plus y squared over 4. R is the region enclosed by this ellipse. Okay, so it's the set of all points x, y such that x squared over 9 plus y squared over 4 is less than or equal to 1. With an equation, that would give me the boundary ellipse, and then the inequality fills that in. Okay. You'll notice I started over here on this side of the board. I'm just always in the habit. I put my UV plane over here and my XY plane over here to remind myself that the direction of the transformation is from UV to XY, even though the direction that I'm going to be going is backwards. So what I want to do is I want to try to find some region in the UV plane and some transformation that's going to send it over. Because I really am not crazy, even though this is both type 1 and type 2, I'm not crazy about the sorts of limits of integration I would get if I worked with this. And switching to polar isn't so helpful because that's not a circle, it's an ellipse. Okay. But I think of an ellipse as a morphed circle. So I'm thinking maybe we could let S be the unit disk so that it's the set of all points UV such that u squared plus v squared is less than or equal to 1. And I can let T be the transformation that does the morphing, that stretches things in both directions but by different amounts. So let's see. If I look here, the horizontal axis is the u-axis. Here it's the x-axis. And we've essentially stretched things by a factor of 3. So what if we were to let x be 3u? And then v was the vertical axis. Now y is the new vertical axis over here. Looks like we've stretched things by a factor of 2. So what if we were to let y equal 2v? Well, let's just check. If I were to plug that in to this inequality here, that would give me 3u squared over 9 plus 2v squared over 4 less than or equal to 1. Holy cow! 9u squared over 9 plus 4v squared over 4 less than or equal to 1. U squared plus v squared less than or equal to 1, which is exactly the inequality that describes the unit disk. Now that we've gone through that algebra once, you may now just take this as it works. So I can view this elliptic region as just a morphed disk, and the transformation is just the thing that does the morphing. It stretches things horizontally by one factor and vertically by another. Excellent. Okay, so now this is kind of nice also because I got the transformation in terms of x and y, so I don't need to solve for them this time. All right, so this is going to become the double integral over S. We're going to have to write our integrand, we're going to have to put our scaling factor, and then dA in the UV plane. Okay. X squared we just said was 3u squared over 9, plus y squared we said was 2v squared over 4. That we just saw is going to become simply u squared plus v squared. Okay. Now do be careful, we're not just working on the circle where that would be constant at 1. We're working on the disk where u squared plus v squared does vary. So we do need to keep it that way. Now what I'm going to put here is the absolute value of the Jacobian. So let's calculate our Jacobian. That's going to be the determinant of the partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. Remember, the transformation takes us from uv to xy. What we're going to corresponds to the rows. What we're going from corresponds to the columns. It's dorky, but everyone gets one R. So to the row, that's one R. From the column, that's one letter R. Okay? All right, and that puts them all in the right place. Okay. So let's see. That's just Partial of x with respect to u is 2. Partial of x with respect to v is 0. Partial of y with respect to u is 0. Partial of y with respect to v is 3. That determinant is 6 minus 0, which is 6. And the absolute value of 6 is also 6. So my scaling factor will be 6. I absolutely believe that you can do this in your head, but I encourage you to write it down, because by writing that you're taking the absolute value, you're thinking about it every time, you're much less likely to forget in the times where it actually affects your answer, because the determinant that you get is negative. Okay, so I'm going to now, since that's constant, I'm just going to factor that out. So we've got the double integral over s, 6 copies of u squared plus v squared, that's what we said that simplifies to, dA in the uv plane. Now usually, if I'm integrating over a disk, I would switch to polar. So let's switch to polar. Okay. U and v are just names. There is nothing sacred about the names x and y. I can totally switch to polar. U is in the role that x is usually in, so I'm going to let it be r cosine theta. V is in the role that y is usually in, so it becomes r sine theta. They're just different names for rectangular coordinates, and I know how to switch from rectangular to polar coordinates. So this is going to become 6. We're integrating on the unit disk. Theta is going from 0 to 2 pi. R is going from 0 to 1. U squared plus v squared, that's usually, I'm used to thinking of that as x squared plus y squared, but it's just this variable squared plus that variable squared, that's r squared. And dA becomes r dr d theta. So we've got 6, integral 0 to 2 pi, integral 0 to 1, r cubed dr d theta. So that's 6, integral from 0 to 2 pi, r to the 4th over 4, evaluated between 1 and 0, and then we'll integrate d theta. That, of course, is just going to give me 1/4 minus 0. So I'm going to get 6 times 1/4 times the length of that interval, which is 2 pi. So I'm going to get, I can cancel, I'm going to get 3 pi. Okay, pretty cool. All right.